introduce yourself?
I'm Patricia Cleary, and I'm an assistant professor of geosciences and an atmospheric chemist.
And I'm Steve Hogan. I'm a professor of geosciences at Indiana University, Pennsylvania, and I study dust for a living.
Yeah. So it's interesting that we both study the atmosphere, but I study processes in the modern atmosphere that relate to pollution events and air quality.
Yeah, and most of my work is ancient. We're talking tens of thousands to hundreds of thousands to millions of years of what the atmosphere was like and the large-scale changes in things that affect climate and ocean circulation.
Mm-hmm. So even though my main research right now is measuring ozone near Lake Michigan or over Lake Michigan, I need to look at air quality models to understand what my measurements mean and also what my measurements can tell everyone about how we understand how air quality is impacted by, regional effects.
Yeah, and I use models in a very similar but slightly different way in that we use models of what's happening today to try and make predictive models of what things were like when the climate conditions were very different in the past. And even though directly I don't model the atmosphere, the data that we collect, where the winds were, how strong the winds are, they get input back into those models to test those models and to improve those models or to verify the models. And so there's a lot of very similar crossover in the modern atmospheric models and the ancient climate models that involve the atmosphere.
Mm-hmm. So I think when I think about a model, I usually think about the model output. There's a map, there's colors on it, there's arrows or other things that describe where the air is flowing or where the ozone is. But when you think about model construction, we have this kind of idea about that it's a box. You have some sort of defined space where you have inputs of either numbers, you usually might call those either parameters or boundary conditions that go in, and then inside your little box, then reactions happen or processes change those inputs into outputs. And when you build models and you stack up different layers where here this has the ocean and then the atmosphere may interact with the atmosphere, and so inputs and outputs can go in between the atmosphere and the ocean. So that looks pretty stark. It doesn't look like there's a lot of stuff in there, but it takes a lot of work, it takes a lot of computation to piece together boxes into an understanding of the whole Earth.
Because I mean, some of those models now that take into account regional and global changes are looking at tens of thousands of little boxes. The upper ocean is influencing the ocean below it, influencing the ocean to the east and the west and the north and south of it. It's interacting with the atmosphere above it, and that little bit of the atmosphere is interacting with those pieces surrounding it and above it, and all those things have different things going on. And so there's an amazing amount of information that's involved in making the calculations to successfully predict what has happened or what is happening or what will happen from those models.
And I think that for us, we remember a time when maybe televisions weren't HD TV and video games were things like Pong, where even a circle didn't really look circular. It had these little edges around it because it was what we call pixelated. And that's because the information could only be shared into these tiny little boxes. And as those boxes get smaller, the patterns show up much smoother. And so you see that same thing in global climate models, where when the boxes are big, the northern hemisphere might just look like one big green square. And now the northern hemisphere is highly detailed, and you can see shorelines and all of that.
I mean, in a lot of ways, I think the models have developed to the point where they've been refined enough and the resolution's high enough that you can see the differences that we all know exist in society. You don't lump everybody as an American. There are different types of American people. There are different cultures, different ethnicities, different styles, different standards of living, and all of that variability gets lost if you just say you're an American. But the same thing with the models is that if the more and more high resolution the models get, the more you can see those differences, and you can predict what those differences are going to be in the reality of the atmosphere, or the reality of the oceans, or the reality of the Earth system.
Mm-hmm. But let's talk about the limitations of models. So, can we know everything about a model? Like, for example, for what you study dust that ends up in ocean cores, right? Can you say that, well, this dust came from a dune that was in the middle of China and I got blown out to sea during this one event?
Absolutely not. And that's actually one of those things that you have to remember about a model. It's a representation of what we think is real. And there are a lot of limitations on what we know about the system that will say, okay, if we don't know this part well, then the output doesn't work as well as we want it to be. And that's what the verification about models and data are all about, is that you use data to predict whether models are working properly, and you use models to predict things that the data can't necessarily tell you, because we can't collect data from everywhere on Earth every time, every day, all the time.
Mm-hmm.
And so they work together really nicely.
Yeah, I think the same thing happens in air quality models, where we talk about having the right answer for the wrong reason. So you can use your outputs and say, well, we predict that there's going to be high ozone over Lake Michigan, and we see that there's high ozone over Lake Michigan. But what we've put inside the model to make that happen, is that really correct? And so you can use other indicators as inputs to make sure that you understand the processes that get you to those outputs.
And I'll just say one last thing about models, is that an old instructor who made this point over and over again, is that if you put garbage in to the model, you get garbage out.
Yeah.
And so I think it's vitally important that you have very good data sets, real data measurements to make sure that models are valid and that they're working properly.
Absolutely.
Thank you.
Sure.
Sweet.